Alright guys, last week we discussed how we could determine the empirical formula of a compound or the molecular formula of a compound. Generally, we could do it from knowing the number of grams of each element in that compound. So for example, we did a lab in which we formed magnesium oxide, and we realized how many grams of magnesium there were in that compound and how many grams of oxygen there were in that compound. We knew the number of grams of each, and therefore we knew the number of moles of each element as well. And knowing the number of moles of each element, we knew the ratios of one versus another, therefore the empirical formula. Now in another lab, or actually in a homework question, and we'll see more like this, we had compositions, percent compositions of each element. So for example, we're told the percent composition of carbon in an element is 37%. Well, we need to find the empirical formula from that information. Well, we can go from the percent carbon, 37% carbon, and assume that we have, say, 100 grams of that carbon. We could assume, therefore, that we have 37 grams of that element, carbon. In another homework problem, we were told that we had 24 grams of sample, and that the percent oxygen was 16%. And so we could find the mass of oxygen in that sample by multiplying the 24 by 0.16. In all of those cases, if we needed to find empirical or molecular formula, we had to know the number of grams of each element. Now, today we're going to be discussing elemental analysis, which, again, allows us to know the number of grams of each element in a compound, and therefore the empirical and then the molecular formula. And so elemental analysis is actually quite complex and uses expensive instrumentation. Back in the lab where I used to work, we used to ship our stuff all the way to Arizona to have an elemental analysis because it can be very expensive. But this problem discusses finding the empirical and molecular formula of isopropyl alcohol. So isopropyl alcohol which is a hydrocarbon. That is, it's got carbon, hydrogen, and oxygen as well. It is combusted in this instrument. So it is combusted in this instrument. That is, it reacts with oxygen at a very high temperature. So the original sample has oxygen float over it, and therefore we're going to presume that it reacts 100% at this very high temperature. And this 100% combustion results in the formation of carbon dioxide and water. In fact, we presume that all of the carbon turned into carbon dioxide and all of the hydrogen turned into water. Later, that carbon dioxide is absorbed in a carbon dioxide absorber, and the water is absorbed in a water absorber. And so, knowing then how many grams of water are collected, and knowing how many grams of carbon dioxide are collected in these absorbers, we're able to know how many grams of hydrogen were collected and grams of carbon were collected. And because we're going to assume that we had a 100% combustion of our hydrocarbon, and we collected 100% of the water and carbon dioxide produced, if we know the number of grams of hydrogen collected, we know the number of grams of hydrogen that were originally in that sample. Similarly, if we know how many grams of carbon were collected in the absorber, we'll know how many grams of carbon were originally in that sample. And so we know the number of grams of 2 of our 3 elements. We still don't know the number of grams of oxygen. Now, you might think that you can find the number of grams of oxygen that were in your sample originally by seeing how many grams of oxygen are in the water and carbon dioxide absorbed. However, this is not an accurate way or a reasonable way of determining how much oxygen was in the original sample. because oxygen is added in excess, we're flowing lots and lots of oxygen over our sample, and there's a lot of oxygen leaving the instrument anyway. So in fact, the only way that you can know the amount of oxygen in your original sample is through a little bit of algebra. And so you know the original mass of the sample, and you can find the number of grams of carbon that were in that sample and the number of grams of hydrogen in that sample. If the only other element left in that sample was oxygen, then you're able to find the mass of that oxygen. The mass of the oxygen is equal to the total mass of the sample minus the grams of carbon in that sample minus the grams of hydrogen in that sample. And so again, I just want to repeat because this is a common mistake. The number of grams of oxygen is not found from the number of grams of carbon dioxide collected or the number of grams of water collected. Not directly, anyway. Instead, the number of grams of oxygen is found by knowing the total mass of the sample and then subtracting the grams of carbon and hydrogen. And so we're able to find the number of grams of oxygen, and knowing the number of grams of carbon and hydrogen, we can do that by a little bit of stoichiometry. So say in our problem that we collect 0.561 grams of carbon dioxide. You can know how many grams of carbon were in that sample by realizing the number of moles of carbon dioxide that were there, and therefore the number of moles of carbon. For every 1 mole of carbon dioxide, there's only 1 mole of carbon, because each mole of carbon dioxide has just 1 mole of carbon in it. Because each carbon dioxide molecule has 1 carbon. So then you know the number of moles of carbon and therefore the number of grams of carbon. And then to know the number of grams of hydrogen, you need to realize how many grams of water were collected. In this problem, 0.306 grams of water were collected. You can find how many moles of water were collected, and then the number of moles of hydrogen that were collected. For every 1 mole of water which is collected, there are 2 moles of hydrogen collected. Because, well, a water molecule has 2 hydrogens in it. This is a common mistake here. And then knowing the number of moles of hydrogen collected, you know the number of grams of hydrogen collected. And so knowing the number of grams of carbon and the number of grams of hydrogen, you can do that algebra and find the number of grams of oxygen. And so now you know the number of grams of each element. So now you can find the number of moles of each element. So grams into moles, using molar mass for all of these. And so you can find the number of moles of each element. And then you need to divide all of these numbers by the smallest one to determine the ratio of each element to the smallest numbered one. So divide the 0.0128 by the 0.0043. Divide the 0.0340 by the 0.0043. And divide the 0.0043 by the 0.0043. And so you get 3.0, 7.9, and 1.0. Now, how likely is it, do you think, to have a ratio of 7.9 hydrogens to every oxygen? Perhaps if you had a molecule with 79 hydrogens and 1 oxygen, you might have that occur, but that would be very unlikely, particularly in general chemistry. You're probably not going to have such large molecules. More likely, you don't have 7.9 hydrogens per oxygen. Instead, you have, rounded a little bit, 8 hydrogens per oxygen. And so there's a ratio of 3 to 8 to 1. There are 3 carbons per 8 hydrogens per 1 oxygen. And so this gives you the empirical formula, the molar mass, the mole-mole ratio of all of these elements gives us the empirical formula. Now, the empirical formula allows you to find the molecular formula. To convert from empirical to molecular formula, you need the atomic multiplier. The atomic multiplier is the molar mass of the molecule over the molar mass of the empirical formula. We were told in our problem that the molar mass of the molecule is 60.11 grams per mole, and we know the molar mass of our empirical formula is also 60.11 grams per mole, 3 times 12.01 plus 8 times 1.01 plus 16 gives 60.11. And so knowing that our molecular and empirical formulas are the same, we know that the atomic multiplier is 1. And so we can convert now from the empirical formula to the molecular formula. Take the number of elements of every element, the number of atoms of every element in the compound, and multiply it by the atomic multiplier. So 3 times 1 is 3, 8 times 1 is 8, and 1 times 1 is 1. And so we now have the empirical and the molecular formula. And so, you know, you're able to do this. You're able to convert from empirical to molecular formula using the atomic multiplier, because let's see, if the molar mass of the molecule is, say, twice as much as the molar mass of the empirical formula, then the molecule must be twice as large. It must have twice as many atoms. And given that the empirical formula has the same ratio of one element versus another as the molecule, there must be twice as many atoms of each element. So let's just say theoretically that the atomic multiplier was 2, because the molar mass of the molecule was, say, 120 instead of 60. Well, then there would be twice as many of each element. So what you would have is C6H16O2. Of course, you don't want to include this in the notes. All right, so just to certify that you've watched all this, I'd like for you to go ahead and give me smiley face again with exclamation marks. All right, thanks guys for watching. I'll see you on Tuesday.